Welcome to the lesson 20 of industrial instrumentation. In this lesson, we will discuss basically the analytical instrumentation. We will find that the two most important process parameters pH and viscosity. And as you know, the pH is very much necessary for many industrial applications as well as bioreaction and biomedical applications, because in some applications we will find that we have to monitor the pH of the blood, and in some bioreactions we have to purposefully make a particular pH value to have a good growth. And there are numerous applications of measurements of pH in chemical industries. So, keeping all this in mind, in this particular lessons we will discuss pH and viscosity measurements and different techniques of the viscosity measurements, pH particular probe and pH amplifier, what are the should be the typical characteristics of the pH amplifier. All these things will be discussed in this particular lesson. Contents are the definition of pH, why is it necessary to measure pH, pH probe, characteristics of pH amplifier. Now, viscosity measurements, basically we will discuss two types of viscosity measurement. One is capillary method and another is rotating drum method, and some industrial viscosity meter or viscosimeter. In industry it is called the viscosimeter. So, rotating drum viscosity measurements, then we will discuss the capillary flow method. Also we discuss the industrial viscosimeter, which is called Seebold viscosimeter, right. So, definition of pH, you see pH is a measurement of the number of grams of hydrogen ions per liter of solution, right. Mathematically it is expressed as negative logarithmic of hydrogen ion concentration, right. Mathematically can be expressed like this: pH equal to minus log base 10 of hydrogen ion concentration. This is equation number 1, where H plus is the hydrogen ion concentration in the solution. The value of pH can range from 0 to 14, where 0 describes the extreme acidity and 14 describes the extreme alkalinity, right. So, 0 describes the extreme acidity and 14 describes the extreme alkalinity. This is a range of pH, either it will be 0 to 14, and if it is neutral, neither acidic nor alkali, then in that case the pH will be 7, like distilled waters has a pH, supposed to be have a pH of 7. Now, pure water or distilled water has a pH of 7. As pH values change by 1 unit, then the acidity or alkalinity values change by a factor of 10. The pH scale is shown in figure 1. You see, next figure you will find these are pH scales we have seen. You see here, so this is, you see, 0 strong acid, and this is a strong base. Base and alkali, as you know, it is same thing, and pH 7 is neutral. As I told you, in the distilled water, strong acid like our acids, or inorganic acids are very strong acid. In that case, pH will be very close to 0 if it is not 0, right. Similarly, alkaline like any alkalis like sodium hydroxides and other types of solutions will give you a very strong base. And as I told you, distilled water should have a pH of 7. Here in this scale, you see here in this scale, we will showing you the hydrogen ions. It starts from 1 to the minus 4. In this sense, we are showing the OH ions. When the OH ions are strong, we will call it strong acid. When the hydrogen ions are strong, so we are calling it and it's other way. When the ions are becoming weak, then it is becoming the strong acids. When H ions are strong in this way, because it is decreasing these directions, it is a strong acid, right. So, it is 1 here, so it is 10 to the minus 14 here. Now, why is the pH measurement is important? That is at the initial stage I told you once. Let me discuss this in details. Measurement of pH of a solution is necessary to judge whether the liquid is acidic, alkaline or neutral, right. It is necessary in many applications, because in some environments we will find that we have to make those environments neutral. So, that type of, suppose the drinking water, it should be neutral. So, in that case it should be neither acidic nor alkaline, right. In some reactions, like suppose in the bioreaction it will be slightly alkaline, so there also the measurement of pH is necessary. In biomedical applications we will find that the measurement of pH is necessary, because we can monitor, by monitoring the pH we can tell some of the particular diseases also. The application areas are food, beverage industry, aquarium, agriculture and gardening and color photography, etc. There are numerous applications, more applications like the industrial applications, as I told you earlier. The measurement of pH of liquid is necessary in many condensate systems as a check on corrosion in pharmaceuticals and drug production for maximum yield. As I told you, in the bioreactors we always make, suppose the yeast cultures, we always make the pH slightly alkaline, right. So, that type of situations we call it, the measurements of pH is also necessary. In food manufacture, because we have seen that if we make it slightly alkaline, so we will find the growth will be better, right. So, that reason measurement of pH, continuous monitoring of pH is necessary for any bioreactions. In food manufacture, to reduce the spoilage and improves the taste and innumerable chemical processes, you will find the applications of measurement of pH. The continuous monitoring of blood pH is essential for the proper treatment of the patient suffering from metabolic and respiratory problems, because the blood has a pH, varies from 7.35 to 7.4, okay, that is 7.35 to 7.5. So, if this for a normal healthy person, now if this goes out of this range, that means patient has some problems. We can monitor those and appropriate actions can be taken, appropriate drugs to be given to the particular patients, so that the pH value comes to the actually normal healthy person's range of 7.35 to 7.4 or 7.5. The pH values of some common substances is given in table 1. Let us look at. You see, this is the pH, the values of some common substance. Battery acid, which is supposed to be a very strong acid, sulfuric acid, you see it is almost close to 0.3, okay, very strong acid. Lemon juice 2.3, okay, because these are all organic acid, is not it. Vinegar 2.9, orange juice organic acid 4.3. So, more and more you see it is increasing in value of pH, right. Then we have boric acid 5, corn 6.2, milk 6.7, slightly acidic, that means distilled water 7.0. Now, it is, if it goes crosses 0, then you will find crosses 7, that means it is become acidic, alkaline. Blood 7.5, as I told you, its range lies from 7.35 to 7.4 or 7.5. So, we have given the value 7.5, right. Sea water is alkaline, is 8, baking soda 8.4, milk of magnesia 10.3, ammonia 11.4, okay, is quite highly alkaline. You can say bleach is even higher, is 12.6, right. This is the range of the pH values for the different commonly used substances. Now, pH probed, because pH is usually, you see that is the, you need a probe and details of the probe is to be discussed. The traditional method of indicating hydrogen ion concentration is the use of litmus paper. This we have seen in the chemistry laboratory, the people use the litmus paper to know whether the solution is acidic or alkaline, but this method is very much qualitative method of measurements. It will not give you how much strong that it is acidic, how much strong is it is alkaline. So, some measurement is necessary, but litmus paper obviously people are using over the years, over the decades, and it gives actually some indications whether the pH value is either the liquid is either acidic or alkaline. So, traditional methods of indicating hydrogen ion concentration is the use of litmus paper that does not give exact value, it is qualitative measurement, as I told you earlier. So, we need some quantitative measurements which will give you the exact value of the pH. Functions of the electrode. What is the function of this electrode? The pH measurement method requires that an electrode be immersed in a solution, obviously, and an electrolytic potential is produced or developed at the electrode, which forms an electrolytic half cells. This is called the measuring cell. There are two cells you will find, one is reference cells and is measuring cells, right. Now, each of these cells we are calling it half cell. There are combined pH probe also, that will be discussed later on. Now, we will first discuss the measuring cells and reference cells. What is the content of this? A second electrode is required to provide a standard potential, and to complete the cell it is the reference cell, right. The algebraic sum of the potentials of the two half cells is proportional to the concentration of the hydrogen ions in the solution. Actually, we want that two voltage will be algebraically added, and we will get the value of the pH, right. The measuring glass electrode is shown in figure 2. So, we will show you the figure. You see the glass electrode. We will first discuss about the glass electrode, then we will go to the figure. It operates on the principle that a potential is observed between two solutions of different hydrogen ion concentrations when they are separated by a thin glass wall. This should be, I am sorry, it should be wall. This potential is function of two concentrations. A buffer solution is contained in the permanently sealed glass electrode, which is surrounded by the solution whose pH is being measured, right. The buffer solution has a constant hydrogen ion concentration, and the potential at the electrode therefore depends on the hydrogen ion concentration of the measured solution. You see, this is our measuring glass electrode. You see here, everything is very much clear. You can see is the electrode lead, this is a glass envelope, we have a platinum wire, and we have a buffer solutions here, right. We have a buffer solutions here for pH measurements. Now, the liquid junction is provided by a small hole in the electrode over which a ground glass cap is placed. Thus, the potassium chloride slowly escapes from the electrode into the measured liquid, and the potential at the reference electrode is also a constant. pH is a temperature sensitive process, process parameter. So, you must compensate for any change, because if the temperature changes, pH value also will change. So, the output voltage of the meter also will change. So, that you must make some compensation for this temperature change. Consequently, a temperature error must be compensated, any temperature error must be compensated. A simple octet is incorporated to make this compensation. The pH electrode can be placed in the vessel or in the liquid pipeline. Either it can be placed in a vessel in which we have to take the sample of the liquid, or in the liquid pipeline where the liquid is flowing, that can also be used to make the measurement, right. The glass calomel electrode can be used as at liquid temperature between the 1 degree centigrade and 100 degree centigrade. You see the reference electrode. The calomel electrode is in the common use as a reference electrode. The calomel is a mercury and mercurous chloride is contained in the inner tube and covers a platinum wire. A saturated solution of potassium chloride is in contact with the measured solution that surrounds the reference electrode. You see, this is a calomel's reference electrode. Okay, we have a ground glass joint here. This is put on some solution, so that it should remain, it should not dry up. We have you see Hg and HgCl solution, okay, and this is a glass envelope, and this electrode lead is coming, and this is a KCl solution, right. Now, combined pH probe, because you see using two probe, it's obviously it's a problematic in many cases. So, we want something very handy. So, that type of electrode is a combined electrode. So, you will find most of the application nowadays, in fact, in our country Philips is making that type of probe, that which are, but other companies are also making. Those are separate, two separate electrodes you have to put. Otherwise, you can have a one combined electrode. That means both reference electrodes and the measuring electrodes are in the same system. Okay, it's very handy, it's very useful, and ease of measurement will be also be there. The most common forms of pH measurement is the combined pH probe, which is shown in figure 4. You see, we will show the figure. This is, you see, the combined electrode, right. You see, it is a connecting cable, and you see here there is pH sensitive glass membranes. Okay. This is not response to glass body. This is non-responsive glass body. We are written here non-responsive glass body, right. So, there is no interaction. So, even if we have a liquid up to this, okay, suppose we have a liquid up to this, okay, in which suppose in a beaker we put this, electrode. So, obviously what will happen, you will find that this will not act, but this is the pH sensitive. You see this glass is pH sensitive, right, it will react with the, so the liquid, it will react with the liquid outside, right. So that because it is filled with the reference solution, okay, so I will get the measurements. And here you see in this case the reference, this is the reference electrode and it is put on a reference solutions, right. This is totally separate, this unit is totally closed, it is not, okay. So only the electrodes are coming out. You see the here the electrodes are these lines is going out. Similarly, this line also, this is the reference electrode line, this is going out. This is a combined electrode, you will see mostly this is the things people are now using. It is the same thing, excuse me. You will find here that there is also reference electrode, reference solutions like KCl solutions are there, potassium chloride solutions. And you see this is our measuring electrode. The same thing is there, that platinum, whatever you have we have seen in the separated electrode, it is already there, but it is combined in two, okay, combined in one system. The combined glass probe consists of a glass probe containing two electrodes, a measuring one and a reference one, separated by a solid glass partition. The reference electrode is a screened electrode immersed in a buffer solution, which provides a stable reference EMF, and it is usually 0 volt, right. Reference electrode is a screened electrode immersed in a buffer solution, which provides a stable reference EMF, and it is usually 0 volt. Let us look at again. You see here there is a buffer solutions here, okay, you can put, this is a buffer solution, this is filled up with the solution, sorry. Okay, you see there here we have a solution, right, that is a buffer, I mean solutions, right. So there is a reference electrode, fine. So reference electrode is a screened electrode and immersed in a buffer solution, which provides a stable reference EMF, and it is usually 0 volt, right, no problem, fine. The tip of the measuring electrode is surrounded by a pH sensitive glass. Again, let us go back, make it will be more clear. You see, this is the tip of the electrode, this is the measuring electrode, this is the reference electrode, okay. Let me again go back like this one. So this is our measuring electrode, it is coming here. This is all those platinum business here. Here you can see here, this is the reference electrode, okay. This you see surrounded by a pH sensitive glass membrane, clear. The tip of the measuring electrode is surrounded by a pH sensitive glass membrane at the lowermost end of the probe, which permits the diffusion of ions according to the hydrogen ion concentration in the fluid outside the probe, clear. Outside the probe we have some liquids, right, you see outside the liquids. So what will happen, you see here, so we have a liquid here, obviously, as I told you, here I have a liquid, but there will be no reactions, this liquid cannot go inside. Here you will see there is the diffusions of the hydrogen ions, okay. So it will react with the this probe, so we will get some output, clear. So tip of the measuring electrode is surrounded by the pH sensitive glass membrane at the lowermost end of the probe, and which permits the diffusions of ions according to the hydrogen ion concentrations in the fluid outside the probe. Actually there should be a full stop here, anyway. The measuring electrode therefore generates an EMF proportional to pH, because other thing is constant. So because it is electrical circuit, I need at least 2 lead, that is the reason reference electrode is also necessary, right. So measuring electrode therefore generates an EMF which is proportional to the pH of the liquid in which that measuring electrode has, or measuring tip has been inserted, clear, because the measuring tip is to be inserted there, so that I will get some EMF which is proportional to the pH of that solution, okay. And the reference electrode, so we got 2 terminals, we will get a voltage that is measured, and that will be converted to the current later on. The characteristics of glass electrode are dependent on the ambient temperatures with both 0 drift and sensitivity. This already we have discussed, because it is sensitive to the temperature. So we have to take proper care by RTD or any other temperature sensitive devices to make the correction. Thus the temperature compensation is needed, okay. It is normally achieved through the calibrating the system output before use by immersing the probe in the solution at a reference pH values, right. That is a very interesting thing, because I can have a reference pH values, suppose solutions of known pH I will put insert, so I can make necessary corrections, or I can have a temperature compensation scheme also by which I can make the correction, right. This is some analytical, that means we have some, because normal I know that it is pH is suppose 4, now it is coming 4.2, accordingly I can make the corrections, because this 4.2 due to some temperature, okay, temperature change. So, that can be corrected for any unknown measuring value of the pH, right. Now, range of pH measurements, you see the typical range for measurement is 0 to 12, because it cannot, it is very difficult to measure beyond 12, okay, it will becoming so much of alkaline, it is very difficult. The electrode contaminations at high alkaline liquid becomes a serious problem, okay, electrode can be contaminated at a high alkaline liquid and becomes a serious problem. The glass starts to dissolve in acid solution containing fluoride, and this represents a further limitations of the use. That is for the lower range, even though I am saying 0, but we cannot measure the pH value of 0, it is very difficult, right, it is highly acidic. The voltage output of the pH probe, you see, because we will get a voltage, the net potential in the pH probe is given by these expressions, right. V naught equal to minus 2.30 RT by F log of CH by CR, equation number 2, where R is the universal gas constant, which is 8314 joule per kg per mole per Kelvin. T is the absolute temperature in Kelvin. F is the Faraday's constant, it is 9.647 into 10 to the 7 coulomb per kg mole, and CH is the hydrogen ion concentration in solution, and CR is the concentration in glass electrode. So, this will cancel, these 2 units will be cancelled out, and that is not, that is the reason it is not mentioned, right. So, we will get the voltage output. If I plug in all the values, I will get which is 1.0 for one normal HCl. Inserting all the values, the output voltage can be expressed as V naught equal to minus 1.98 10 to the minus 40 in pH units. So, pH units you can see is a very small, right, it is sensitive to temperature. So, that is the reason T units is there. Now, pH amplifier, you see the pH amplifier should have a very typical characteristics. The pH, since we have a glass electrodes, we can consider it as a voltage source. It is like this one, you see that we can consider as a voltage source. That means I have a voltage source, okay, and with a high source impedance, right. So, any current, if I try to draw some current through this circuit, because when you measure with this resistance by some meter, okay, it has some input impedance, is not it. So, a current will start to flow if you connect this one, suppose this is a meter, then what will happen? There will be large drop across this, okay. So, I won't get the proper measurements. So, the pH amplifier that should have the basic characteristics of the pH amplifier, that it should first of all is a DC amplifier, and amplifier means actually it is amplifying and also the measuring the voltages output of the pH probe, which is coming from the reference and the measuring electrode, because measuring electrode is one point, measuring 2 electrodes are there, okay. If I take separately 2 electrodes are there, so this voltage is to be measured between this point and this point, right. If it is combined also it is same thing, because this also 2 separate, and 2, as I have seen the 2 electrode leads are coming out even in the combined electrodes. So, we have to measure these two, this voltage between these 2 electrodes, and since we have a glass, so it is source impedance of this we can consider as a voltage source, and because of it glass, it has a very high internal source resistance, right. That is the reason we cannot get any voltage. You see, this is very common. You see, those who are most familiar with our dry cell batteries, because I am giving the examples of dry cell batteries because it is almost all of us we have seen that when the dry cell is almost dead, you can see almost, suppose it is supposed to be for normal healthy dry cell, it is 1.5. Now, after use over the suppose days and months, you will find the dry cell voltage drop, but you will look at very interesting, that is the voltage does not drop much. And surprisingly, if you want to draw some current, you will find that you are not getting any current. The reason is due to chemical reactions inside, the dry cell's internal impedance has increased so much that you cannot draw any current from that source. right? That is a voltage source, is not it? A dry cells is a voltage source of 1.5 volt. Now, initially this resistance is so small that you cannot measure a current, you cannot measure short circuit current, it is very high, right. But as the time grows, there is a chemical reactions and you will find that internal impedance initially it is very, very small, and initially after use you will find this voltage, this internal resistance is getting increased. At some level you will find that you cannot take out any current from that voltage source, right, because the internal impedance is so high. Similar the case in the case, because of pH probe, because of its internal, because of the glass probes, internal impedance is in the order of several megohms. So, I need some amplifier. First of all, I have to amplify that signal, which is very small, okay, DC signal, and I have to amplify the signal, as well as the main characteristics of this amplifier should have a very, very high input impedance. That means, looking from this terminal, if I look at, okay, looking from this terminal, the impedance, the amplifier, the impedance, the meter or the amplifier will offer should be extremely high, at least 100 times higher than the source impedance of the 100 times higher than the source impedance of the pH probe. Clear? So, let us look at the details. The pH probe has a source impedance of the order of 100 megohm, because the electrode is made of glass, right, fine. A very high input impedance DC amplifier is a good choice. The input impedance of the amplifier should be of the order of 10 to the power 10, 10 to the power 12 ohm. You can think of it's 10 gigohm to 1000 gigohm I want, right. This much of higher impedance is necessary to measure the pH. How will I achieve that high value of the, because you know that we have studied so many amplifiers and these that, okay, we know that if you use a, suppose if you simply use those who are from electronics, you must be knowing that if I use a common collector amplifier, a single transistor common collector amplifier, I will get a higher impedance than the common emitter or common base amplifiers. We can have we can have the op amp also, suppose in the unity gain feedback mode, which is obviously used as many applications we have seen in the instrumentation, it is used as a buffer amplifier, right. Or I can use cascade amplifier also, which will give you the higher input impedance, but this input impedance is not that high that I can measure the pH voltage, right. So, we need some other applications like MOS devices, FET devices at least, or MOS devices. In fact, in the case of FET, as you know, the input impedance is very high. In the case of MOSFET, input impedance is even higher. So, we should have some devices of some circuit by which I can achieve this much of input impedance, right. Let us look at details of that. An instrumentation amplifier should be made of op amp which has a high input impedance differential stage, right. So, instrumentation amplifier which is to be made of op amp. So, instrumentation amplifier is that its input impedance is higher than the op amp, and its common mode rejection is also better. So, keeping all this means you can have but first of all I need op amp, very high quality op amp which is high gain as well as high input impedance, extremely high input impedance, otherwise you cannot measure. Please note, op amp should be preferably be made of MOSFET input differential stage, and it is implemented in BiCMOS. BiCMOS, as you know, CMOS is complementary metal oxide semiconductor, is a bipolar complementary metal oxide semiconductor process, by which we have in the same wafer we should have a both bipolar devices as well as MOS devices, and this type of amplifier will give you the proper impedance which we can utilized, that amplifier can be utilized to measure the pH voltage. This will lead to an input impedance of 10 to the power 12 ohm. You can see 10 to the power 12 means almost 1000 gig ohm, right. Now, analog devices AD 5449 op amp is such a devices which can be utilized, safely utilized for measurements of pH value, right. Now, this all we talked about this pH value. Now, let us come to the another analytical measurements which is called the viscosity. Viscosity is also very important because in many applications you will find that the quality of the food product also depends, viscosity quality of the chocolates depends, and depends on the raw materials. So, the people try to measure the viscosity of that. Suppose the glycerin which you are producing in the industry, they also measure the quality, because basically it is for the quality control. Okay, in the process industry you will find basically for the quality control. In food industry these actually give you the good taste. Okay, in some there is restrictions of the pipe, whether if it is very viscous there will be a large pressure drop, I need a large pumping cost will very high. In that type of situation continuous monitoring of viscosity is very much necessary, right. Let us look at now absolute viscosity is defined as tau equal to mu dV by dy, this is equation number 3 in continuations of the PE, this that is the reason I have given the equation number 3, where tau is the shear stress between the fluid layers in laminar flow, which is in Newton per meter square. Mu is the dynamic viscosity, is Newton second per meter square, and dV by dy is the normal velocity gradient as indicated in figure 5. I will show the figure 5. You see this is the our relations of viscosity gradient and the fluid shear. Okay. So, this is a tau equal to mu by dV by dy, right. This is this is V, I think, and this is Y. So, this will be V, I think. So, this will be V, this will be Y, right. Let me see. This is a Vy. So, I am sorry. So, if I go back, so this will be V and this will be Y as it is, no problem in that, right, right. So, mu k or kinematic viscosity we defined as mu by rho. Okay, another terms we defined also, that is the absolute viscosity or dynamic viscosity. Absolute viscosity, this is absolute viscosity. People sometimes say this is the I am sorry. So, units for kinematic viscosity would become Newton second meter per kg, right. That means you have to divide the absolute viscosity or dynamic viscosity. Mu is the absolute viscosity or dynamic viscosity, that is to be divided by the density of the liquid, you will get the kinematic viscosity, right. These units obviously will be different. Now, some of the more common units are given below along with the appropriate conversion factors. What are the different units? Even as I told you that those SI units not very popular in industry for me, expressing the viscosity. Let us look at all the different units. Dynamic viscosity, you see dynamic viscosity or absolute viscosity is given as 1 Newton second per meter square equal to 10 Pascal, 10 poise equal to 1000 centipoise. Okay, it is defined as Cp, then equal to 1 kg per meter second. Okay, meter second is in the denominator. 1 poise equal to 100 centipoise equal to 1 dyne second per centimeter square, which is equal to 0.1 Newton second per meter square, right, which is 0.1 kg per meter second. And kinematic viscosity is given by 1 meter square per second equal to 10 to the power Stokes. Okay. This is also 1 Stoke equal to 1 centimeter square per second equal to 100 centi-Stokes. Okay. Most commonly used the unit you will find in the process industry is called the industry, you will find the Cp or centipoise, right, which is equal to 10 to the minus 4 meter square by second. Now, velocity distribution between large parallel plates, we are showing that what is the velocity distribution. Suppose these two parallel plates are there and plates are suppose stationary. Now, suddenly suppose these plates they start to move in this direction, this plate starts to move in this direction. Okay, plate is moving in this direction. Okay, you see this plate is moving in this direction, then what will happen? You see the liquids which is in contact with this one will be moving in a faster direction and liquids which is contact will have no velocity. So, all the liquids have slowly you will find that the velocity distributions will be look like this one. This is highest, this is highest, this is low, this low, and which is liquid in contact with this plate, this stationary plate, this is a stationary plate will be stationary, right, and the liquids which is in corresponds to this all this velocity we are measuring with respect to the stationary plates, right. At the top this will be the highest. The two most common methods of viscosity measurement are the rotating concentric cylinder method and capillary flow method. Okay, these are the two most important method of measurements. This is a very direct electrical output you will get. Okay. Now, rotating concentric cylinder method, let us first discuss this, then we will come to the capillary flow method. Consider the parallel plates as shown in the figure 6. We have shown in the parallel plates shown in the figure 6. One plate is stationary, that means lower plate is stationary and the other moves with a constant velocity v. The velocity profile for the fluid between the two plates is a straight line and the velocity gradient is dv by dy equal to b by b. Let us go back. You see, this is the separation between the two plates, this is b, this is stationary plates, this is a moving plate, you see this is a straight line, right. The velocity profile for the fluid between the two plates is a straight line and the velocity gradient is dv by dy equal to v by b. Equation number 4. The principle could be used to measure the viscosity by measuring the force required to maintain the moving plate at the constant velocity v. The principle could be used to measure the viscosity by measuring the force required to maintain the moving plate at the constant velocity v. The parallel plate system is difficult to construct, however, because you see this type of parallel plate is very difficult. Two plates are moving parallel, it is just because I can have some liquids inside, okay, in between two parallel plates and the plates are moving, one plate is around. It is very difficult to realize. Instead, we can make two concentric cylinders, right. One cylinders I mean stationary, other cylinder is moving, so that we can realize that parallel plates phenomena there also. That will be easier for us to make mechanically to make the construction, right. The parallel plate system is difficult to construct, however, the parallel flat plate situations will be realized with rotating concentric cylinders as shown in figure. The inner cylinder is stationary and attached to the torque measuring devices, while the outer cylinder is driven by a motor at a constant angular velocity omega. Let us look at, you see this is our, right. You see the inner cylinder is stationary and this outer cylinder with a shaft is connected to motor, it is rotating at a constant angular velocity of omega, right. This is shaft. Now, this torque, the torque on this shaft will be measured, right. Inner cylinder is stationary, it has a length of L, okay. This is has a okay, separation between the bottom separation between the two cylinders, right. This is a separation between the that means the inner diameter of the outer cylinder, difference of the inner diameter of outer cylinder and inner diameter of the diameter of the inner cylinder, okay. That is the B, right, and L is the length of the cylinder. If we have, then we can write, if the annular spaces B is sufficiently thin in comparison with the, you see, actually let me go back, actually this will be, so this R2 actually if you look at this R1 will come to this position, right. Now, R2 from the center, R2 will should come to the this one. That means, I should say that R2 is equal to R1 plus B. B is the separation between the two cylinders, okay, separation between the two cylinders, or I should say R2 minus R1 is equal to B. R2 minus R1 equal to B. That means, the inner radius of the outer cylinder minus the radius of the inner cylinder is equal to B. If the annular space B is sufficiently thin in comparison with the radius of the inner cylinder, then the rotating cylinder arrangement approximates the parallel plate situation and the velocity profile in the gap space may be assumed to be linear. Then dV by dy equal to R2 omega by B. Question number 5. Where the distance y is taken in the radial directions, right, distance y is taken in the radial direction, and it is assumed that that B, we have assumed here that the B is B is much less than R1, okay, it did not come. So, B should be much less than R1. If the torque T is measured and the fluid shear stress will be expressed as tau equal to T upon 2 pi R1 square, 2 pi upon T equal to tau equal to T upon 2 pi R1 square into L, right. This is equation number 6, where L is the length of the inner cylinder and the viscosity is determined by the combining equation 3, 5 and 6. What are those 3, 5, 6? Let us look at. The very beginning we have the equation number of yes, this is the equations of the absolute viscosity, okay. So, this equation, then 5, and 6. So, whether this I combine. So, where L is the length of the inner cylinder and the viscosity is determined by combining equations 3, 5, 6 equal to mu equal to T into B 2 pi R1 square R2 square TB upon 2 pi R1 square R2 square L into omega. This is equation number 7, right. If the bottom gap space is small, because then the bottom disc will also contribute to the torque and influence the calculations of the viscosity. Usually it is small. So, the torque on the bottom disc will be Td equal to pi mu pi omega by 2a multiplied by R1 to the power 4. This is equation number 8. So, the total torque due to the bottom and the annulus place, actually that will be measured. The total torque by the some torque cell or torque meter. Total torque due to the bottom and the annulus place will be given by mu pi omega R1 square multiplied by R1 square by 2a plus 2L R2 by B. Okay, this is equation number 9, right. Right. If the torque, now angular velocity, these are all constants. So, if the torque is measured, angular velocity is measured, dimensions of the cylinder, that means R1, R2, L, A, B, these are all known to us, then the viscosity may be calculated from the equation 9, is not it. So, because omega is known, because what is the rotation that we can measure by some our tachometers, we know this is the dimension R1, R2, L, A, B, these are the dimensions of the all the cylinders, that also it is known to us, and we can measure tau T because by some torque cell. So, obviously only unknown is mu, right. So, the viscosity of the liquid, okay. So, please note that liquid is to be filled up, okay, that is the most important thing, that I have not you see, sorry. So, this gap is to be filled up by the liquid, okay, this gap, please look at, this gap is to be filled up with the liquid of which we are interested to measure the viscosity. So, this gap that means in between the two cylinders, inner cylinder and outer cylinder, there is a gap. So, this gap is to be filled up by the liquid by which you will measure, in which we are interested to measure, of which we are interested to measure the viscosity, right. I am sorry. Okay, this so the if I can measure, so obviously from these equations I can measure. Now, there are many other methods. Okay, very conventional methods you will find in the laboratory, physics laboratory. People uses what they use a cylinder, right? A long cylinders, okay, and they filled up the liquids, they filled up that cylinder with the particular liquid in which we want to measure the viscosity, right? We need a large quantity of the that liquid, obviously. Around a liter or something like that. Then they drop a ball from the top, a steel ball, right, of known diameter or radius, spherical ball. So, they are falling. So, they between two particular points of that cylinder, they measured the when they crosses that particular line, top line, they turn on the stopwatch. When it crosses a bottom line in the liquids, they stop the stopwatch. Then what will happen? So, total time of fall by they measure, and from that also, if we know the dimensions of our that ball, we can find the viscosity. It is a very common experiments also, you will find many physics laboratory people uses to measure the viscosity of the liquids. But here the problem is that when the time of fall, you have to measure very precisely. If there is an error, so you will find the viscosity of any known liquid also whichever you are getting. Usually in the physics lab, you will find that they are asked to make the measurement of viscosity of glycerin, right? So, which glycerin is the known viscosity is known. Obviously, you will find that is very difficult to measure, because if the time is short, you will find there is a large error in measurement, right? When the time is short, when the balls will be large, right? When the ball will be large, so it will have a large gravity, I mean gravitational force, so it will have a large mass, so it will quickly, the time of fall between 2 points within the liquids is very short. So, in that type of situations, it is very difficult to measure. It looks like this. Suppose I have a cylinder like this one, okay, like this one. So, they measure, it is a transparent body, so it should be made of glass. So, there is a mark here, there is a mark here. So, we put a steel ball. So, whenever it crosses this mark, I turn on this our meter stopwatch. When it crosses this marks, we stop the meters. We note the distance between these two, right? Distance between these two marks. So, obviously, if this time is large, so there is it is only large when there is a, I mean the ball size is small. If it is large, yes, when the time will be large when the ball size is small, and time will be very short when the ball size will be large, right. So, there is a problem in 2A, but the problem of the time measurement more crucial we found, and most of the time it is very erroneous to measure the time, right. I mean turning on stopwatch and stopping the stopwatch is very difficult. Rather, if we take a small ball and with a of which we know precisely the radius or diameter, we can find that is very easy to, most accurately and almost accurately you can find the viscosity of the liquid, right. But that is a very laboratory experiments, as you can see. It is not you cannot say it is very industrial sort of devices, but its rotating drum method or capillary method is can be utilized in industry for measurement of viscosity. A capillary flow method. In this method, the pressure drop is measured across a capillary tube in which the liquid is flowing in a laminar fashion. Consider the tube cross section shown in figure 8. Renault number is defined as Renault rho, I mean Re, rho Vm by d is a mean flow velocity d by mu. Okay, density of the liquid, velocity of the liquid, mean velocity of the liquid through the capillary, d is the diameter, and mu is the viscosity of the liquid. If the laminar flow exists in the tube, the familiar parabolic velocity profile will be experienced as shown in figure 8, and if the fluid is incompressible and the flow is steady, the volume rate of flow Q will be given by Q equal to pi r to the power 4 P1 minus P2 by 8 mu L, that is meter cube per second, right. You see here the velocity distribution of the laminar flow, the liquid is in contact with the this pipe diameter, inside pipe diameter, there is no motions, and here you will find the velocity is maximum, okay, as a central point, okay, and as you again it goes to the this positions, what will happen that there is no movement of the velocity of the liquid which is in contact with the surface of the inner surface of the pipe. It is similarly. So, this is the velocity profile of a laminar flow of a liquid inside a pipe, right. We are talking of Vm, that is the average velocity, okay, including separate points, measuring and taking the average. A viscosity measurement is possible by measuring the this and very familiar equations all of us know. This P1 is P2 is the two points between which we are measuring the Q. There is a pressure at P1 at terminal 1 and terminal 2. L is the length between the two tappings of the pressures, right. Okay. This is, you see that here we have a pressure tap, we have a pressure tap here also, right, and this is the length between the two pressure taps. Viscosity measurement is possible by measuring the volume rate of flow and the pressure drop or flow in such a tube. To ensure the laminar flow will exist, a small diameter capillary tube is used, and the small diameter reduces the Reynolds number as calculated from equation 10. In equation 10, the product rho v m may be calculated from rho v equal to m dot by pi r square, where m is the mass flow rate, right. Vm is the mean velocity of the fluid inside the capillary tube, and multiplied by rho Ct will give you the mass m dot. You see the m dot is the mass flow rate divided by pi r square. When viscosity measurement is made on the gas, the compressibility of the gas must be taken into account, and the resulting expression for the mass flow of the gas under laminar conditions in the capillaries m dot equal to pi r to the power 4 16 mu r naught t p1 square minus p2 square. R naught is the gas constant. We want to differentiate from this radius, that is the reason this r. So, we have used a different notations. R is actually radius of the pipe or the capillary through which the gas is moving. Care must be taken to ensure that the flow in the capillary is fully developed, that is that the parabolic velocity profile has been established. This means that the pressure measurement should be taken for a far enough downstream from the entrance of the tube to ensure that the developed flow condition presents. It may be expressed that the flow will be fully developed when capital L by D equal to get at the Reynolds number by 8, where L is the distance from the entrance of the tube. Now, in the industrial viscosimeter, you see the Sebald viscosimeter is a very commonly used viscosimeter. Sebald viscosimeter is an industrial device that uses the capillary tube principle for measurements of viscosities of liquid. A schematic of the device is shown in figure 9. A cylinder is filled with the top with the liquid, and the liquid is then allowed to drain from the bottom through the short capillary tube. Okay, let us go back first to the figure. Yeah, this is our industrial viscosimeter. You see, this is to be placed in a constant temperature bath. Please note, these are all the dimensions of this we have given. So, this to be placed in a constant temperature bath, because viscosity, if the temperature changes, also the viscosity changes, and these dimensions is basically, if you look at these dimensions, is around 0.1765 centimeter, just above 1 millimeter, right. This is 0.9 centimeter, this is 0.1765 centimeter, this is 2.46 centimeters. These all the dimensions are given, right. Let us go back. The time required for a given quantity of liquid to drain is recorded, and then this time is taken as indicative of the viscosity of the liquid. Since the capillary tube is short, a fully developed laminar viscosity profile is not established, and it is necessary to apply a correction to account for the actual profile, right. The velocity profile were fully developed. If the velocity profile fully developed, the kinematic viscosity would be vary directly with the time for drainage, that is mu k is kinematic viscosity, which is absolute viscosity upon rho equal to C1 T, right. This already we have shown, right, all the dimensions we have shown here, you can see here, right. See industrial viscosimeter, you see a cylinder is filled with the top with the liquid, and liquid is then allowed to drain from the bottom, right. Right. This is all about our viscosity measurements, and viscosity measurements, as you know, also is very much necessary for industry also. I mean, for quality and the taste of the food also, and both in the food and beverage industry also, this measurement is necessary, and this is very paper and pulp industry is very much viscosity measurement is very much important. we will find that the measurement of viscosity is very much necessary, because as I told you, it reduces the pumping costs of the liquids and the quality and control also, but because it is one of the parameters by which you can make the quality control of your liquid or product. Okay. So, for all these reasons, viscosity measurements are equally important as pH, right. So, with this I come to the end of lesson 20 of industrial instrumentation. Welcome to the lesson 21 of industrial instrumentation. In this particular lesson, we will do some exercises. That means, I will give you some problems and also will provide the solutions. The best way to solve the problem, you first do not look at the solution, first try to solve the problem and then see whether whatever the answer you got it, then that is getting tallied with the results which we have given, right. So, we will particularly solve in this lesson the problems on the LVDT and then pH probe and McLeod gauge. As you know, the McLeod gauge is used for the low pressure measurements, pH is used for the pH probe is used for the pH measurements, and so LVDT already we have covered. So, we will sort different types of problems of LVDT, right. So, let us look at the contents of this lesson. So, these are problems and solutions on industrial instrumentation. The contents are the problems and solutions, LVDT, linear variable differential transformer, pH meter as well as McLeod gauge, right. Problem number 21.4, it problem is telling in order to calculate the pH, the following arrangement is made. A pH electrode is connected through a shielded cable to a non-inverting amplifier as shown in the figure. We will show the figure. The input resistance or impedance of the non-inverting amplifier is given by R equal to Ri 1 plus A naught Rf by R1. Okay, everything will be clear in the circuit. So, let us go back, let us look at the circuit once again. R1, Rf, okay. Now, Rf, R equal to Ri 1 plus A naught Rf by R1. A naught is the open loop gain and Ri is the input resistance of the op amp. Find the output voltage V naught of the following circuit when 225 millivolt signal is generated at the electrode. Shielded cable looks like this, pH electrode, and this looks like this. Okay. So, you see this is buffer amplifiers we have used, supposed to be very high input impedance. So, we have used shielded cable. So, with this I come to the end of lesson 21, where we have solved all the problems.